talk. Can everyone hear me? And apologies for the very strong Scottish Glasgow accent, but hopefully you can parse the majority of what I'm going to say. I arrived here on Sunday night, and someone asked me if I could just pop through to Oxford to examine a PhD on Monday. And little did I know I had to spend 6 hours on a bus to get there and back. So this morning was great, knowing I had about a 5-minute walk to come here and give this talk. I'm going to talk about some work which we've been doing over the last 12 months or so in really trying to develop tools which will allow biologists to reason about their models of various biochemical and biological processes, and in particular biochemical pathways. So let me just say that the whole motivation of this work was really to try and address some open issues surrounding the whole field of systems biology which are related to inference. The very fact that many theoretical biologists are relying on mathematical models of biochemical and biological processes, it would seem reasonable that some characterization of uncertainty in their subsequent reasoning of the study of the systems which the models are describing would be a sensible thing. And so the two main open issues really are, one, given a particular model, a mechanistic model, and in particular what I will be focusing on here are deterministic models based on systems of nonlinear differential equations. And given that the technologies available to measure certain chemical species, and in particular their rates of reaction, is rather immature and in many cases unavailable, a lot of the parameters that define these models cannot be measured directly, and therefore we would like some way, given experimental observation, to infer sort of plausible ranges of the values for these parameters. And indeed, what we would like to do, rather than having point estimates of these, we would like to characterize a distribution, so a posterior distribution, which then can be used to perform subsequent global sensitivity analysis of the model and so forth. The other main question, of course, is that there are many plausible models which can describe a particular biochemical process. And so what we would like to be able to do, again, is given certain experimental observations, to be able to objectively assess the evidential support that a set of potentially competing hypotheses or mechanistic descriptions of a process will have. So we're looking for some way of model ranking. And again, this is to allow biologists a means of then perhaps rationally designing subsequent experiments to test further the hypotheses that underlie their models. So what we would like to then be able to do is somehow or other jointly do some posterior inference over the parameter values of these models, and in addition, in case you were unaware, I'll be taking a Bayesian viewpoint here, is that we would also like to obtain estimates of Bayes factors to assess this evidential support. And the manner in which we do this, or we ended up doing this, is by using what is typically called the thermodynamic integral. And I know some of you in the audience are more than familiar with this. And we take a stratified path sampling strategy to obtain estimates of this in obtaining estimates of the integrated likelihood, which is required for the Bayes factors. And I will present quite a large-scale application of this methodology to the extracellular regulated kinase signaling pathway. From here on in, will just be referred to as the ERK pathway. And we have some very exciting results from the experimentalists based on this, so we'll look at that at the end of the talk, and then I'll conclude and we can ask some various questions. So I should also point out that I've designed this talk to give to some biologists as well, so just bear with me if I go through some statistics 101 in a bit too much detail. So here's a typical mechanistic description of, in this case, a nonlinear dynamic system which describes the circadian control of, well, in this case, we have a number of the standard central clock genes, and there's a bifurcation point in this model which then will lead to sustained oscillations. Now, it's possible to measure the levels of these proteins and the levels of these transcripts, these messenger RNAs, but what it's not capable of, what we can't really do, is measure the levels of the rates of transcription or the rates of inhibition in this model. So given that we can measure, or partially measure, the messenger RNA and the protein concentrations, what we would like to be able to do is identify the parameters which give rise to the experimental observations. So in other words, we want to do some sort of system identification or parameter estimation. The other problem then is that we would like to assess the sort of evidential support for competing mechanistic descriptions. So here is the extracellular regulated kinase pathway which I mentioned to you, and typically this is the cell wall, and then there is some growth factor, either a nerve or in this case a epidermal growth factor, which binds to receptors on the cell wall, and then there is a whole pathway sequence of biochemical reactions which lead from the cytosol right into the nucleus, which then activates this kinase protein. And this little cartoon here gives a description which one set of cancer biologists would consider to be a very plausible one, and one which is supported by experimental evidence. On the other hand, here is another description which again is on the table. In this case here, there are in actual fact two parallel paths of reactions which control the phosphorylation or the activation of this kinase. And indeed, there's a third hypothesis which would suggest that in addition to having two paths from the receptor to the activation of ERK, there may well indeed be some sort of crosstalk from a third pathway which in some way or other controls this. So again, what we would like to do is, in addition to trying to infer the parameters of these descriptors, we would like to try and objectively assess some evidential ranking of the support for each of these descriptions. Now, I should point out that there was a red paper in RSS, the Royal Statistical Society Series B, at the end of last year, trying to address the problem of parameter estimation in differential equations. So this is quite a topical problem that's being considered within the statistical community. But I would like to take this a step further and say that parameter estimation is one thing, but what is really important, certainly for the biologists that I collaborate with, is this means of assessing this evidential support. And that then means we have to start to consider the problem of estimating integrated likelihoods. So just to recap, I guess I can skip over this quickly. What we're going to do is exploit the methods of statistical inference to account for the uncertainty and to account for it in a consistent manner. We will try and obtain probability distributions, and in particular posterior probability distributions over the various kinetic rate parameter values, and in addition the distribution over the actual plausible structures which describe these models. So the three main goals will be that, one, we want to do posterior estimation, posterior inference over the model parameters. We would then want to use those posterior distributions to predict possible outcomes of new experiments, simulate knockouts, but again, consistently propagate this uncertainty so that any reasoning about the sort of behaviors that are observed can be, well, conditioned on the levels of uncertainty that are there. And then finally, compare alternative models of the system. And so I'm really going to focus today on this problem here. So again, the key measure that we want to use then is the base factor. We're given two particular hypotheses which underlie the structure of two models with sets of parameters. And given that we've made some observations, then we would like to obtain the posterior odds of the model. Now, of course, what we require is the integrated likelihood under each hypothesis. And the integrated likelihood, as we all know, has been the subject of many PhDs and continues to be the subject of many research problems. So we need to estimate this integrated likelihood, this expectation of the likelihood with respect to the prior over the parameters. And this has to be obtained in a fairly robust way. So let me just consider two very common estimators. One, of course, is that we could just sample from the prior and then just use a Monte Carlo estimate based on the parameters sampled from the prior. This, of course, is a very inefficient estimator, and I'll give a demonstration of that just shortly. So one way of getting around that estimator, the inefficiency of that estimator, would be to use importance sampling. And again, the very classical estimator that is used is that the importance of the sampling function is typically the posterior. And when we plug the posterior distribution over the parameters into our importance sampler, we end up with this very commonly used estimator, which is the harmonic mean estimator. And this is very popular because we can use the output of a Markov chain, if we're using MCMC, to obtain an estimate of the integrated likelihood. Okay. Why is it not a good idea to use either of these in general, and in particular on models which are based on systems of differential equations? So again, if we go back to a very simple linear regression model, we have, I've lost the, there it is. So just it's a standard linear model, linear combination of some basis functions, and we have a Gaussian additive noise term. The prior that we place on the weighting coefficients will be Gaussian, and of course the posterior is multivariate Gaussian with the usual mean and covariance. So this is all standard. So of course it means then that we can obtain an analytic expression for the integrated likelihood, where we've integrated over these the parameters beta. So I'm going to use this as an example. So if I take a finite sample of, say, 30 observations, and each observation consists of between 2 to 20 covariates, and I fix the prior variance and the variance of the noise, and then I generate data from this model, I can then obtain the analytic values of the integrated likelihood based on the number of covariates that are being used. And so if I use the samples drawn from the prior, then we can see very quickly that our estimates, so using around about 100,000 samples here, by the time we get to around about 6 covariates, for this finite number of samples, the prior estimator starts to creep and starts to fail quite considerably. On the other hand, the harmonic mean estimator does much better. So we don't have this explosion of bias and the variance here. It still seems to be, the variance is reasonably well controlled. But what we see, and what's quite interesting to see here, is that there's a consistent overestimation of the integrated likelihood using the posterior harmonic mean. Now, why is this a problem? Well, here's a very simple problem here. Let's consider this nested model. So we have a linear combination of two covariates, and then we have an alternative model which has a quadratic term. Now I'll generate data from the linear model and compute the base factor. So the analytic value for the base factor is 28.3, which in Jeffrey's tariff would suggest that there's very strong evidence in support of a linear model. However, if I look at the estimates of the base factor using the posterior harmonic mean estimator, and what we find is that the estimate suggests that the evidence is really not worth more than a bare mention. So this is somewhat worrying, especially given the simplicity of this nested set of models here. So we shouldn't really trust that. And in fact, what Adrian Raftery suggested was to actually have a mixture model where there would be a mixture component from the prior and a mixture component from the posterior. And that was one way of trying to resolve other problems with the posterior harmonic mean estimator. Well, in actual fact, there was a quite important paper in '98 which suggested a means of path sampling that could provide stable estimates of the integrated likelihood. And in essence, what they do is they devise a path from the prior to the posterior, and we would then integrate right across that path. And here is one example, and there are many other more general forms of this here, where we can devise a path directly from the prior to the posterior. So if we introduce an auxiliary variable t, which is an inverse temperature, and we define this conditional posterior over the parameters of interest, conditioned on our data and the auxiliary variable. This has been referred to as a power posterior by Friel and Pettit in their recent RSSB paper, which just appeared. So of course, if we set this auxiliary variable, this inverse temperature, to 0, then we in essence have the prior, and when t is 1, we then recover the posterior. So some calculus 101 leads us to the sort of standard form for this thermodynamic integral, which represents the log of the integrated likelihood as an integral over the path from t equals 0 to 1 of the expected value of the log of the likelihood with respect to this power posterior. So we have this continuous path from the prior to the posterior, defining the log of the marginal. And methods such as annealed importance sampling and so forth, which is a non-equilibrium based estimator of this, well, it's actually a non-equilibrium based estimator of the likelihood, the integrated likelihood rather than the log of the integrated likelihood. But this is a fairly well-known measure. So we now want to obtain an estimate of this. Well, one obvious thing that we could do is we could just introduce a sampling distribution P of t for the inverse temperature. And we can then write our log of the integrated likelihood as an expectation with respect to the joint distribution, joint posterior of parameters and t. And our Monte Carlo estimate just requires us to draw samples from this joint posterior. So that's fairly straightforward. We can define a Markov chain, which would have acceptance ratios based on these Hastings, acceptance probabilities based on these Hastings ratios. And so if we propose a new set of parameters, then there's no computational problem here. This can all be computed fine. But as soon as we propose a new inverse temperature, then of course we hit this very classical problem that the measures that we're actually trying to estimate now appear in our Hastings ratio. So we have a problem. And there have been methods which have tried to address this, and the original paper by Muller in 2006 used a data augmentation trick, which was quite elegant. And more recently, by Murray, Garamani, and Mackay on improving upon Muller's method have been proposed. There are also techniques based on what are called MCMC without likelihoods, which could be used to get around this problem. So myself and Niall Friel spent a couple of weeks last summer trying to get this to actually work using Muller's method and failed miserably. So we left it there, but just yesterday talking with Arnaud Doucet, he tells me that he has a solution to this problem which is elegant and efficient. So I'll, as soon as his paper comes out, I'll be very interested to see what that solution is. But in the meantime, we are stuck here. So we then have to now consider, rather than sampling jointly from theta and t right across the range of support from 0 to 1, perhaps using discrete approximations or discrete representations of this integral. Now, in actual fact, this turns out to be a virtue, and it turns out to be a virtue based on the fact that we can now stratify the sampling. So rather than uniformly or sampling between 0 and 1, if we discretize the path, then what we find by using standard simple Monte Carlo theory is that the variance of the estimator using this stratified path will be no larger than the variance of the estimator that we would obtain if we were able to get the MCMC working for estimating, or using this estimator here. So if we, as I said, discretize the unit line into a number of subintervals, and within each of those subintervals we then make a number of draws from t, where we've now defined some density within that strata, and then given t we draw samples from this power posterior. Then our Monte Carlo estimator, well, in the standard form, and some statistics 101 shows that the variance of the stratified sampler should be a lower bound on the variance over the overall sampler. So actually having to consider discretizing this integral, as I said, there may well be virtue in this, in that we can obtain a superior estimator in terms of the variance of that estimator just by stratifying this path. Okay, so in that case then the log of the integrated likelihood can now be written, the thermodynamic integral can now be written in terms of these conditional expectations. I should also just point out that from here on in, I'm assuming that the sampling distribution for T within the strata is uniform. So it's just 1 over the length of the discrete element. So we have this conditional form for the thermodynamic integral. And again, the corresponding Monte Carlo estimator follows fairly simply. And the interesting thing is that if we, rather than taking a number of samples from each of the strata to obtain the expectation with respect to T, we just use the 2 endpoints, the lower and upper endpoint, then what we end up with is this approximation to the thermodynamic integral, which was proposed by Friel and Pettit in a draft technical report in 2005 and in their RSSB paper, which has now just appeared 3 years later. And also completely independently by Lartelot and Philippe. I know some of you are familiar with this work, where they were looking at estimating integrated likelihoods for phylogenetic trees. So we have this discrete approximation, which for those of you who are, well, it's fairly straightforward to see that this is just a trapezoidal approximation of the integral over the path. So we're now moving away from obtaining an unbiased estimate to an estimate which in actual fact is an approximation. So how good is this approximation? Well, some simple algebra allows us to write the integral in terms of the sum of the expectations of the log likelihood with respect to the power posterior conditioned on the temperature or the inverse temperature at the lower points of the strata, plus this term here, which is the Kullback-Leibler divergence between the posterior at T sub n minus 1 and Tn. And this actually turns out to be a lower bound on the integrated likelihood. We can do the same and define an upper bound, which again defines this upper bound based on the Kullback-Leibler divergence, this time between the posterior at the upper temperature and the lower temperature. And of course, averaging these together, we end up with the trapezium approximation and the residual bias, which is now just going to be the difference in the asymmetry of the KL divergences between the posteriors at either extreme of the strata. So we now see that if we can define a path between 0 and 1, so we define a series of these discrete elements which controls this bias, then we can obtain an approximation which will minimize this bias. Now, of course, it's fairly straightforward, and it's been published in numerous papers, that we can obtain an estimator which will minimize the variance of the estimator. And if we just consider the continuous case, then an unnormalized density over T is just going to be proportional to basically the posterior variance at each of these temperatures. And this is a fairly standard result. Now, if I go back to the linear regression model, I should also point out that this talk is a bit like Bunyan's pilgrim. I started off talking about nonlinear ODEs and how we're going to do inference over those. And I spend quite a bit of time talking about how we obtain estimates of integrated likelihoods, but eventually we get back to the main topic of the problem. So just bear with me while we're in bypass meadow for the time being. But some tedious algebra actually allows us to get an analytic expression for the optimal sampling distribution for T between 0 and 1. And here are some examples here for models with between 2 and 20 covariates. Now, you see here that the prior variance is set to be, well, it's absolutely huge. And then we start to tighten it up to quite ridiculously small values. But the key point here is that all the sampling should really be done, right, very close to the prior. So in other words, if we were to discretize this, what we should be looking for are strata which are very, very small at the prior and then start to elongate as we move out to the posterior. Okay, so if I then, based on this here, this would then suggest a means of selecting, well, I mean, we could actually estimate this in some sense, but we could just have, given a finite number of strata, we could have a partitioning which, as I said, defines some sort of power representation. We have very small saltus here, and then they start to get larger as we move up to the posterior. And here's an example of a representation where, again, we're using this linear regression model, and we're using a model with 2 covariates and one with 20 covariates. We are using a number of estimates using different levels of discretization from 10 partitions up to 100 partitions. And in this case, we're using a quintic power representation. So all of the, in this case, 10 or 20 partitions are really squeezed up close to the prior. So if I look at this example here with 20 covariates, what you see is the upper bound estimate and the lower bound. And this is the trapezoidal approximation. And this, of course, is the analytic value of the marginal likelihood. And likewise for a model with just 2 covariates. So we can see that very quickly, I mean, certainly by the time we've got to 100 partitions, we're getting very nice approximations with reasonably low bias. If, on the other hand, I use a uniform partition, and so that is basically the same as just the standard Monte Carlo estimator. This is the upper and lower bounds and the trapezoidal approximation that we get for the 2-dimensional linear regression model. So this one here. So you can see that the errors are really huge. Right? So the biases are really, really enormous. And even as we go up to 100 partitions, we are still really poorly performing in comparison to using this sort of power-like discretization. Okay, so this is all good. And here are some examples, again, for the linear regression model. So we can see the poor estimates that we obtain in terms of bias and variance for the prior estimator. The posterior harmonic mean estimator is much better, but it still has this systematic bias. And worryingly so that the variance is very tight around the bias estimate. However, if we compare these posterior harmonic mean estimates to the estimates that we obtain from the thermodynamic integral, we can really see, even with only 1,000 samples across the full range of the temperature ladder, we're getting very, very encouragingly good and low biased estimates. Now, what that means, if we go back to the original problem of computing the base factors for a set of nested models of a linear and a quadratic regression, we now see that the base factor for the linear versus quadratic model is certainly much more appropriate, and would certainly suggest that the evidence is indeed strong in favor of the linear model. Okay, so that's great. We now have a fairly straightforward means for obtaining this estimate of the integrated likelihood. Now let's return to the sort of main topic of the talk. And here's an example which we're working on, in fact. So a very simple dynamic model of an oscillator. And in fact, this is a much more simplified representation of the circadian oscillator that I showed you in cartoon form right at the very start of the talk. And so here we just have some feedback from a protein which inhibits the production of this mRNA. And this can be written just in terms of a system of nonlinear differential equations. So the inhibition of the production of this mRNA and of course the rate of decay. And there may well be a whole sequence of intermediate proteins, right, which mediate the activation of this protein here. Now if I take the most simplest case, it's just one intermediate protein, and I look at two of the parameters, and I plot the likelihood surface, then we get a likelihood surface that looks like this. Now, it's comforting that the maximum of the likelihood happens to be and there's a very strong peak at the correct values that generated the data. However, the likelihood surface is far from smooth, and it's quite interesting that these kind of curves of equal likelihood are actually caused by the fact that there are series of parameter values which would give the same phase and amplitude of oscillation. So you have these sort of ridges of equal probability. And this can cause, and in fact does cause, major problems for any sampling procedure because of these ridges. And if I just run Metropolis, a Metropolis sampler on a simple oscillator model, then we can see that the chain doesn't mix at all well, and here's one example where the marginal posteriors are just way off the true values. So of course one standard technique for getting around this problem is to use methods like parallel tempering, where we would have as the target distribution the product of a series of tempered distributions. So in this case here I have the prior, and then a series again of tempered distributions where the likelihood is now starting to enter into the definition of the tempered distribution in a similar way to what was shown earlier on. So this of course then allows us to define a Markov chain where we would have moves between these distributions, and then this, parallel tempering is a standard technique which gets round the problem of poor mixing for likelihood surfaces or posteriors like this here. Now if you think about what we're doing in computing the discrete form of the thermodynamic integral, we're defining a path similar to this here. Then we're running a Markov chain at each one of these temperatures, and then at equilibrium we're using samples from those to compute those expectations that are required. And once we have those expectations, we can stitch them together to obtain the integrated likelihood. Of course, the problem now is that for distributions here and here, we're now going to have very, very difficult problems in terms of getting samples which are reflective of this particular distribution. So of course what we can then do is we can use something like parallel tempering, or what's probably more popular now, population MCMC, where there are more than just exchange moves between tempered distributions. We then obtain samples from the desired posterior, but we also obtain samples from each of these intermediate posteriors, which we can now use in obtaining our integrated likelihood. And so this then is something which again Friel and Pettit suggested in their recent paper, a nice way of using techniques like parallel tempering where the intermediate distributions are in fact key to estimating the integrated likelihood, rather than just intermediates that are used to obtain good mixing up at the posterior. Now, just bear with me, I should, yeah. And so, a nice illustration which non-statisticians like is, here is 20 metropolis samplers, and you can see, their start and then they stop exploring very, very quickly. It's really very poor. Whereas the sampling from the prior, an intermediate distribution, then up at the posterior, we get a nice exploration of the overall posterior. So now, of course, we get appropriate estimates. So our posteriors are now centered on the true parameter values. So we get round the mixing problem. And of course, we're getting an estimate of the integrated likelihood. So we are able to jointly obtain the posteriors, which can then be used for global sensitivity analysis in our model subsequently. And we get an estimate of our integrated likelihood, which we can then use. And here's a simple example, just to illustrate the point. So two simple models of an oscillator, one with no intermediate protein and one with a couple. And so what we'll do is we'll just generate data from each model and then compute the base factors in a pairwise manner. So what we'll do is we'll estimate the integrated likelihood using the thermodynamic integral by just using metropolis sampling, and then we'll use it by we'll estimate it by using proposals, exchange proposals between the intermediate distributions. And it should come as no surprise to you that the estimates of the base factors, when we just rely on a series of independent intermediate distributions with no exchanges, the variance is, well, it renders these estimates pretty useless. On the other hand, if we do have exchange moves within our temperature ladder, then the variance of our estimates of the base factors are down at reasonable levels, which allows us to have a reasonable confidence that we could now use these in assessing the support for these competing models. Okay, so let's go to the ERK signaling pathway. Now, I mentioned to you in the introduction that there were a number of plausible structures which are being considered. And the task that we were set by our collaborators at the Beatson Institute for Cancer Biology in Glasgow was rather than investing 3 months of experimental effort in assessing whether this branch actually existed or not, can you develop models of these and then use your base factors to assess which one of these is best supported, if either of the two is best supported. And then given that, we will then go and design some experiments to assess that. So there were a number of, okay, so let me, as I've spoken probably too long already. So in essence, we can represent these pathways as two systems of nonlinear ordinary differential equations. There is of the order of 50 parameters, so this is quite a substantial size model. There's about 20 to 25 systems of ODEs describing each of these pathways. Actually, this is a very interesting problem on its own, because if we do some sensitivity analysis of these models, we find that there's many parameters which are actually insensitive, but that's another another piece of work. So we were able to obtain a PhD student generated data by measuring, so given stimulus from various components of this pathway, measurements of the levels of active ERK were measured in a time series. And so, for example, activation, so a stepwise perturbation of EGF, and then the response of ERK to that perturbation was measured over a certain time period. And then psilocybin, so a perturbation of the activation of psilocybin, again the response of ERK was measured, and so forth. PKA agonist and various perturbations around the whole system were measured. Now this took almost a whole PhD to produce this data. And to cut a very long story short, and to, well, suffice to say that it took one PhD to obtain posterior estimates for these models and to obtain estimates of the integrated likelihoods. The bottom line was that this particular dual pathway model had overwhelming support from the data that had been measured. So given that, experiments were then designed where both these species here were knocked out one at a time. So using small interfering RNA, this was knocked out, and then the level of active ERK was measured. CRK was knocked out, and then both of them were knocked out. So if the predictions based on base factors were correct, then we should see the appropriate drop in levels of active ERK. And much to my relief, that's exactly what we see. So when Greb2 is knocked out, then the levels of this active ERK drop from a very high level to a low level. And likewise, on the left-hand path, when CRK is knocked out, the level of phosphorylated ERK dropped. And then just to confirm things, both pathways were knocked out, and the level of ERK then dropped to the basal level. So this was very exciting, and this is currently under submission to a paper that our cancer biologist colleagues consider to be significant. But it was very exciting in that this was I mean, these experiments could have been designed without us actually doing the modeling, but it was a proof of concept and a proof of principle that using mechanistic models in the form of systems of ODEs and then doing the appropriate statistical inference can actually provide a useful means for guiding and designing subsequent experiments. I'm not going to talk about some recent work that we're doing about improving the computational efficiency of sampling, but I'll just conclude by saying that a number of you are more than aware that estimating base factors, especially for these nonlinear ODE models, is extremely challenging. And we can obtain stable estimators using this sort of path sampling strategy from the prior to the posterior. This is using an equilibrium, so each of the Markov chains have to reach equilibrium, of course. And if we use product space sampling, so either using some sort of population MCMC, then we obtain both a characterization of the posterior of the parameters, which again is something that's very useful in terms of the global sensitivity analysis of the models, and we obtain fairly stable estimates and low variance estimates of the marginal likelihood. And we've demonstrated this on quite a substantial model, a biochemical model, and it's generated an awful lot of excitement amongst various cancer biologists. And our current work now is really looking at how we can use auxiliary stochastic processes such as Gaussian processes to remove the computational burden of every time we have to generate a likelihood, we have to solve a system of equations. And these models are usually stiff systems of equations, so there's a huge computational bottleneck in generating likelihoods. So we're doing some work now where we're using Gaussian processes to try and sidestep the explicit solving of the ODEs and generating a likelihood. And I guess that's probably everything. There is some software which Microsoft funded the development of, and a number of biologists are now currently using, which uses this thermodynamic integration computing integrated likelihoods and base factors. And I'd just like to acknowledge some PhD students and my various collaborators who worked with me on this particular project, and the good people from EPSRC and MRC who funded this work. So I managed to talk for less than an hour, Mike, I think. So.
How long did it take you to collect the experimental data?
It was about 3 years. So despite the MCMC taking of the order of months, it kind of puts it into perspective that
So would the real confirmation be labeling the chemicals and looking at the flux?
well, that's what was done in this experiment. That's exactly what they've done. That's the flux that's been measured.
So there are sort of two aspects to why base factors are sort of hard to use. One is the computational aspects you talked about, and the other is that they can be extremely sensitive to the settings or priors in the model. So how hard did you have to work to sort of go in and really understand what you already knew about biology and sort of setting all your hyperparameters in all your models?
So there's a huge, okay, so that's clearly something that I skirted over, and I gave this a similar talk to the statistics department at UCL, and I got asked the exact same question. So it's extremely important. What I didn't discuss was the fact that there was a huge amount of sensitivity analysis that had to go on and take place. And so the answer is that we really have to, if there is anything that we know about any of the parameters, then we really have to use that to inform our priors. So what we haven't done as yet, just because of the sheer amount of time that this work has taken us, is then to start considering how sensitive the results are to our choices of the priors. But it's something that we're certainly working on.
So you're not sure if you're like that factor of 10 to the 6, how much might that change by?
Indeed, yeah.
In these two models, they could potentially have different data, because the one on the right has some additional variables in it.
Yes.
So the base factor can only, it's a likelihood of some data, but it has to be the same data.
Yes, which it is.
So you can do it for the data which all the models describe,
Yeah.
but if you wanted to know about that path there, wouldn't you want to measure that data? And in that case, what can the other models say about that data?
Yeah, so of course what we're doing here is we're now integrating over all those species that we're not observing. So the only thing that we've observed here is the target at the bottom, which is common to both models. So what isn't common to both models we haven't observed?
Are you saying that the number of parameters in both models is the same, or it's more in
No,
one?
it was
So making a
50 and
comparison
55.
between models with different number of parameters.
Yeah, but we're integrating over those, so we're just, all that we're wanting is the probability of the measured levels of the concentrations of ERK given that structure and given that other structure.
Given that the base factor was so spectacularly high, was it not obvious, or would they have been totally shocked if it had come out the other way around?
Yeah, so, okay. When we embarked on this work, rather than looking at asymptotic approximations, such as BICs or what have you, we felt that we should go for the gold standard and try and compute the integrated likelihood, because if that didn't work, then we wouldn't have much chance. However, subsequently, the likelihood on its own at the maximum values is also very much tipped in favour of this model. So,
mentioned Rafferty's suggestion of doing the sampling with a normal mixture of the posterior and prior. Did you try that?
No.
Or why not?
Because my hands were full just trying to get this to work. But actually, there was a paper in Bayesian statistics just either in the middle of last year, I think it was either 2006 or 2007, where Adrian Rafferty and various co-workers looked at other fixes to the posterior harmonic mean. And again, even if you look at some of the estimates, that you still see this overconfident bias. So we didn't. I mean, one of the things that we did use was annealed importance sampling, which worked a treat.
I was going to ask more about that. So in your description, you have these temperature levels, and then because you don't mix at the very low temperatures, you do this random walk up and down the temperatures. And annealed importance sampling deterministically changes the temperature. So you don't have
it just
sort of
pops up and down.
slow random walk. But on the other hand, you might need more temperatures for it to work, and it's not clear which is better. I wonder if from this experience you've got.
Yeah, I mean, we've done. We've done some comparisons, and so what was appealing to us for this particular problem was that the chains with annealed importance sampling don't need to equilibrate, and I'm sure you can appreciate that it's hard enough to get chains, even intermediate chains, to equilibrate here. So that was something that we thought was very advantageous as far as annealed importance sampling was concerned. Of course, we would then expect that there would be a higher level of variance in the estimates, but the fact we've actually just published a paper where we do a comparison between annealed importance sampling and this sort of strategy, and there's nothing really much in them, as you would expect in many ways. So in terms of normalizing over computational cost, they were both pretty much similar for all intents and purposes. But what you don't get is samples from the posterior, from annealed. If you're not equilibrating the chains, then